If you want to understand the digital circuits, at the very first stage, you have to understand the binary switches. This is a switch. Here is the input and here is the output. And from there, the switch is being controlled. Here, the switch is currently open. So when the switch is open, whatever in the input, there is no output. When the switch is closed, whatever values are in the input, you can find it in the output. Since the switch has only two states, on or off, we can say that it's a binary switch or just a switch. And this switch has three connections. One is input, another is output, and control. When the switch is closed, the light is on. Let us say on equal to 1 and off equal to 0. And we denote the state of the switch with a variable x. When x equal to 1, that means the switch is closed. When x equal to 0, that means the switch is open. Using this simple logic, we can say the state of this light S equal to x. That means when x equal to 1, S equal to 1, that means the light is on, and when x equal to 0, the light is off. Let me connect two binary switch in series. This is one switch and this is another switch. This switch we say X and this switch we say Y. In, out. We just denote the output of these switches as F. So in that case, F you can get the output only when the two switch is connected at the same time. Otherwise, the input will not pass to the output. So in that case, we can write F equal to X and Y. That means the both in switches need to be connected to get the output. We can write F equal to X dot Y or F equal to XY. All are same. This is the AND operations, and the gates symbol of the AND is like this. Those twos are inputs like X and Y, and here is the output. It's like F. This is called AND gate. Here is the practical AND operations. Like this switch and this switch are connected in series according to this diagram, and I can say this is X and this is Y, and the output, I will get the output from this LED. So for AND operations, both switches need to be connected at the same time, otherwise the output will not get from this LED. X and Y, then I will get the output, otherwise not. To formally represent the operations of a AND gate, we can use a truth table. This is the truth table I'm making for AND gate. This column is for input X and this column for input Y, and I'm getting the output from this column F. So as this is two values for the input, and then we can get 4 possible inputs like 0 0 0 1 1 0 and 1 1. So when X and Y both are 0, output we getting 0. When X 0 and Y 1, we will get output 0. The same when X 1 and Y 0, also we will get the output 0. We will get the output 1 only when both inputs are 1. So in that case we will get 1. So this is the truth table. Of AND. This is the truth table of AND gate. If we connect two switch in parallel, and you want to get the output from there, so in that case, either any of the switch connected, you can get the output from here. Either X or Y, just need connect or just need close only one of the switch to get the values from the output. So in that case, we can say that this operation is OR operations. We can write F equal to X or Y, and we can write as well the same thing, X equal to F equal to X plus Y. This plus indicating OR. The symbol of the OR is like this. Here I have connected two switches in parallel according to this diagram, and then I'm getting the output from this LED. So either one of the switches, if on, so the LED will be on, and this will be the OR operations like X or Y. Any of these two switches, if on, the LED will be on, and that looks like the OR operation. X or Y, X or Y. The inputs and outputs of OR gate, we use the truth table of OR gate. This is X and Y, and this is the F of output. Also we have four possible values of two inputs: 0, 0. When we put 0 and 0 in inputs, we will get 0 to the outputs. Any one of these switch is closed, like 0, 1, we will get the output 1. Any one of this switch is closed, we will get the output 1. So when both switch are closed, like X and Y are 1, we also get the output 1. This is the truth table of OR gate. NOT gates, just the symbol is like this. Its function is whatever you put in the input, you will get the output inverted. So in that case, F equal to X prime, or F equal to X bar. This is the NOT operations in practical. So the input is currently 0. You can see this resistor is connected to the ground, or the negative terminal of the power supply, and from the switch, one is connected directly to the switch from the positive terminal, and then when I press the switch, this and this wire will be connected to the positive power supply. That means this will connect directly to the positive power supply. Now I can say that this is currently is 0, because from this base of the transistor, this end and this end of the switch is connected to the ground. So now this is connected to 0. For NOT operations, the switch, when I press the switch, that means when I put the input 1, the output will be 0. Looks like that. You can see I put 1 to the input and I get output 0. So when I put 0 to the input and I am getting the output 1, that means the LED is on. So 1, 0. 1 0 1 0 1 0. So this is the NOT operations. Again, to formally visualize the operations of a NOT gate, the truth table for NOT gate is, as there is only one input, we can say X, and one output, this is F, and we have only two possible values for this input. One is 0, another is 1. So when X equal to 0, the output is 1, and when X equal to 1, the output is 0. So this is the truth table of NOT gate.